Thank you all for being here. I'm really excited to be here. This talk is going to be in English. I hope nobody minds. I'm going to talk to you about how we used web technologies in an entirely different context to reduce ship emissions. My name is Charles. I work for Sirena, which is a subsidy of Naval Group. So we build some of the most precise and fuel-efficient dynamic positioning systems in the world, and we also make unmanned surface vehicles, ship stabilization systems, and maritime surveillance systems. The people in our industry work daily in a very harsh and hostile environment, and when we design our systems, we never forget that human lives are often at stake, which is why the maritime industry is very conservative and risk-averse. However, today it faces economical challenges, regulatory challenges, and ecological challenges. And it faces those challenges using technology. And this requires a substantial effort in research and development, which is why the European Union helps us by funding collaborative research projects, such as Leanships, which is the subject of this talk. Sirena's role in Leanships was to design an application to reduce ship emissions. It's a decision support system, and I'll explain a little bit what this means. But just how big of a problem are we talking about when we talk about ship emissions? Well, to give you an example, this is the Victoria First. It's a ferry going from Stockholm to Tallinn and back. And it's the ship on which we are going to install our system next month. Now, this ship burns 30 tons of fuel a day, every day, 360 days a year. And the company that owns and operates it, Tallink, has 9 ships, such as this one. So fuel consumption is obviously a problem, and any gain, however small, in fuel consumption can have substantial impact when you multiply by the number of ships and the number of days at sea. But why do we need software to reduce ship emissions? Well, that's because it's a difficult problem. The emissions come from burning fuel. The more fuel you burn, the more gas you release in the atmosphere. And about 70% of the fuel we burn on the ship is used to, well, move the ship forward at a certain speed. And, well, just like a car is more or less efficient depending on the gear you're in, well, the ship's propulsion depends on its configuration, how many engines are on, how you're using the propeller, and so forth. And so the ship has to overcome a certain resistance, which is due to the simple movement of a body in the water. And the resistance is also due to, well, the weather, so the wind loads, the waves, and the current drift. And the weather itself depends on the speed, because if you change the speed, well, you reach a different point at a different time, and so you don't encounter the same weather conditions. So this is Leanships. Now, you can see that we have, well, it's meant for a laptop, so obviously on such a big screen you won't be able to read very well, but you have a map with the various voyages that we're comparing. And on the left you've got the list of voyages that we're interested in with the fuel consumption for each one. And so if I move a waypoint here, well, you'll see that the fuel consumption updates in real time. Now that fuel consumption here takes into account the weather along the way. So we're actually simulating the ship's voyage and with changing weather conditions. So, well, we can change the speed along the way for each waypoint, and when I change the speed, well, I change the fuel consumption, and I can also change various parts of the ship configuration. So, well, our philosophy when we designed this tool is to, we don't want a black box system where we automatically give the operator the best possible route, because the operator has a lot of implicit constraints in his or her head that we cannot possibly put in this tool. So what we want is the machine and the human to augment each other by allowing the operator to focus on what he's good at, which is having an overview, detecting patterns, and the software has to focus on what he's good at, which is performing calculations in real time. And what we want is that the software becomes an extension of the operator's mind. So that's what we're striving to do. So comparing voyages is all very fine, but you also have to know, well, what's happening on your ship in real time. And so for this, we use, some of the 300 sensors that are on board the ship. So this is information that's updated in real time, depending on the sensors that are on board, and they give an overview of what's happening on the ship. And so we have the future, and we have here the present, and we also have the past, where for each trip we can generate a report that synthesizes what happened on that trip, the fuel consumption, and so forth. So we have 5 main parts in this software. So we have, the models. Those are the people who work out what the ship's behavior is going to be when you put it in water, and what the engine, how you model the engines and the fuel consumption. You have the sensor people. Their job is to integrate 300 sensors on board and provide information in real time. The weather people, they need to work out what weather model to use, and depending on the part of the world we're in, what the granularity of those models, and depending on what we want, wind, wave, current. The map, so we've got tens of gigabytes of data that we have to render in real time with a tile server. And the interactivity, which, as I mentioned, is the cornerstone of this software, because without it, you won't have any engagement, any user engagement. So all of these 5 parts correspond to different domains, each with their experts, their tools, and language. And somehow we have to have a cohesive whole with all of this. And by the way, all of this has to run on this laptop without an internet connection. So what we're seeing here is that we're shifting context from the embedded world, where we've got a single domain where we're solving familiar problems using our own tooling that we designed ourselves for a single operator, and where safety is paramount, where we absolutely must not endanger the personnel, to a context where we're building, a non-critical system, because we don't operate the ship, we don't change the engines or the propulsion on board, but we have to accommodate a variety of users across a whole spectrum of problems using the work of a variety of partners, because we cannot possibly develop all of this ourselves, so we have to use the power of the community. So our paradigm is shifting from safety first in the embedded world to, move fast, because we have lots of things to integrate, and reduce the risk inherent to, integrating all those things. So, how do we move fast and reduce risk in a, very traditional, risk-averse environment? My bet was by using unfamiliar, bleeding-edge technology that wasn't designed for our industry at all, so web technologies. Now, I'm going to walk you through 3 stages our application went through before becoming what it is today. So, we started with, an architecture style that I dubbed Pew, so Python, Elm, and WebSockets, and hopefully this isn't as stinky as it sounds. So, we used Python for the backend because it allowed us to reuse our existing C++ code and all sorts of libraries that cover pretty much all the domains that we're interested in. And for the front end, we have a variety of users, because depending on the phase that you're in, if you're planning the trip, if you're watching in real time, it's not the same people who are going to be doing that. So we're going to be on different platforms, and building a Qt application C++ application doesn't quite seem like a good fit for that. So we wanted a web app, and well, somehow vanilla JavaScript didn't quite resonate well with, well, safety first and reduce risk and so forth. So we used Elm, which is functional language, strongly typed and statically typed, which compiles to JavaScript. This means that we've got no runtime errors, or our errors happen at compile time. The types mean that it's easy to refactor, it's very easy to test, and we have no side effects, and the compiler actually checks that we cover all our cases, which is very important. All of this has to somehow communicate, and we use WebSockets for that, which is communication protocols which allows 4 duplex communication channels over a single TCP connection. So that means that, well, the communication can be instantiated from either side, and we don't have the overhead of HTTP because the headers are only sent once per session. So this allows us to move fast with the stack and reduce risk. All of this runs on a single virtual machine, which, well, allowed us to abstract the hardware away because, well, we could evolve the hardware without changing our code, basically, unlike what we did in the embedded world. But after a few months of doing this, well, this virtual machine became a problem, of course, because, well, it was an unmanaged state. So we were back to pre-version control days, and it really became difficult to work with. So, and hard to deploy because, well, we had to have the right machine to do it. So what we decided to do was to put all our services into their own containers. So now, the same way we abstracted our hardware using virtual machines, we abstract our platform and dependencies using Docker. So it means that we can move much faster and much more safely because, well, we know exactly what we're doing, we have no conflicting dependencies, and we can build increasingly complex stacks by layering the Docker containers above one another. And we can rebuild everything from scratch. We just need a computer with Docker, make, and a good internet connection, basically. However, after a few months, something horrible started happening. This started happening. This is a picture of the monolith in Curlos, and it's a picture that I took in Brittany, and my daughter here gives a sense of scale, and you cannot help being overwhelmed by a sense of awe when you look at this and you think, how did ancient, primitive people put together this code base? And that's exactly what we thought when we looked back at our code, and we said, well, no, I mean, it's not because you put your services into the containers that you have magically arrived into microservice heaven. What's going to happen is that the coupling and the dependencies between your services are going to bring your monolith back together in a kind of giant zombie monolith overlord that's going to slow you down. As well as that, as we had point-to-point communications between our services, well, we had to have service discovery, and that adds complexity because, well, you have to configure it, all the services have to have access to it, and although it works on scales like the scale of Netflix, well, on a single laptop computer, it did seem a bit of overkill to have, well, all that boilerplate. And also, well, we're in a synchronous world, so failures propagate because the client has to deal with all the possible errors of the server. So what we did is we moved to an event-oriented architecture. So now all our services are completely decoupled, and we can add services dynamically. So we can add functionality dynamically at runtime. And also interesting side effect of moving to this architecture was that it forced us to clarify well, the interfaces and what was exchanged between the services, because if you don't do that, what you end up is a great big fat mess, basically. And, well, trust me, I've been there, I've done that. And so this also meant that failures do not propagate, because failures are literally a non-event. So if you have a failure, well, you just don't emit an event, and so, well, it just stops there. You have to log the failure, of course, so that you can monitor it, but the user won't be impacted by a strange failure that it doesn't, that he or she doesn't understand. So in 2 years, we went from a single application running on, well, close to the hardware in C++, to full-blown event-driven microservices, and abstracting away the hardware, abstracting away the platform, with, well, asynchronous communication between the services. So this, by the way, the last bit was the hardest to achieve, because it required rethinking our algorithms. If you have an optimizer to write, well, it's easy to write synchronously, but pretty hard to write asynchronously. So what did we gain? Well, low coupling between our services, each team working on our various parts, so the model, for example, or could stay with their own tools, and we just thought about the interfaces. We had access to a wealth of third-party tools and libraries. Our system is more resilient because failures do not propagate, and we develop much more quickly. Now, the question that might arise there is, isn't this a little bit of overkill for an application that has to run on a single computer? Well, if you're only building it once, it probably is. But what we did is that we took the opportunity of this research project to, well, learn about all these technologies that we did not know, and then we reused them across the company in various projects. And so there it becomes worth it, because, well, as you're learning, you're not going to be as efficient on this one project, but when you're going to do your second and your third project, then it is going to be worth it. So now our challenge is, well, we've went from the embedded world to the web, and the question is, can we go back? Can we bring back some of the things that we learned in the web back to the embedded world? Can we, for example, run Docker containers in mission-critical embedded software? How do we handle cybersecurity and so forth? And those are, well, today's challenges and the questions that we're asking ourselves today. And we've only just begun tackling those challenges. So, well, I'm happy you could join us for this journey, and I'll be more than happy to answer questions in English ou en français. And thank you very much.